This vast terraced excavation represents the physical and economic scale of an iron oxide copper gold, or IOCG, province. These are multi-generational assets capable of supplying the global copper and gold markets for decades. Yet exploration teams routinely fail to locate them. A primary reason for this failure is an industry-wide tendency to treat the IOCG classification as a single, static geological model. When geologists apply a one-size-fits-all approach to targeting, they end up mobilizing highly funded drill campaigns based on isolated copper anomalies. The result is millions of dollars spent drilling barren rock because the underlying vectors were misaligned with the subtype's specific signature. To build an accurate targeting model, we must split this conceptual monolith into 5 distinct subtypes: regional, magnetite, hematite, breccia, and REE. Each branch is governed by different fluid chemistry. They possess unique structural traps, alteration sequences, and distinct geophysical footprints. Navigating this complexity requires adopting a 10-parameter systems thinking framework, a method of evaluating the deposit not by its surface expression, but by the mechanics of how it formed. Precise drill targeting demands that we abandon surface-level anomaly hunting. We have to deconstruct the entire geological machinery, tracing the system from a deep crustal source all the way to a shallow structural trap. On this 3D continental margin cross-section, IOCGs require ancient Proterozoic basement architectures. At the base, deep magmatic intrusions provide the thermal engine and metal inventory. But these metals are useless trapped below. They require crustal-scale shear zones acting as vertical conduits for ascending magmatic fluids. Opening these pathways requires immense tectonic stress. The continental crust must physically fracture, tearing open solid basement rock, allowing highly pressurized fluids to escape upward. The fluids ascend until they hit the trap. These are structural intersections, or dilational jogs, where the pressure suddenly drops, causing the fluids to pool and rapidly precipitate their suspended metals. Because the fluid conforms to available space, the specific geometry of that structural trap ultimately dictates the physical shape and orientation of the final ore body. Without this exact alignment of a magmatic source, a permeable pathway, and a depressurizing trap, significant IOCG mineralization is physically impossible. Without these mechanical constraints, there is simply no mechanism to concentrate metals into an ore body. As fluids travel upward, their pressure, temperature, and composition evolve. This evolution forces the fluids to diverge, creating the fundamental split between the different IOCG subtypes. The magnetite subtype forms first. It is the product of early-stage, highly reduced fluids interacting near the deep mafic intrusion boundary. This dark, heavily crystalline specimen is the direct result: a dense, iron-rich magnetite ore body holding precipitated copper and gold. On a geophysical survey, this map shows exactly how that dense iron registers. The magnetite subtype produces perfectly coincident high gravity and high magnetic anomalies. If the fluid continues to push higher into the shear zone, it cools and becomes highly oxidative, forming the hematite subtype. These oxidative fluids are aggressive. They actively attack and destroy any early-stage magnetite shell they encounter, chemically replacing the iron structure with hematite. This vibrant reddish-purple sample proves that transition. The iron remains, but intense oxidation has converted the mineralogy from magnetite to hematite. Notice how this chemical replacement alters the geophysical target. Because the magnetite is destroyed, the hematite subtype registers as a strong gravity high, directly overlapping a distinct magnetic low. That specific pairing of heavy gravity and low magnetics is the exact signature that led to the discovery of world-class assets like Olympic Dam. Tracking the fluid's oxidation state is critical. An exploration team relying strictly on magnetic highs will interpret a magnetic void as barren rock, walking directly past a massive, disguised hematite system. Sometimes, extreme pressure creates extreme structural variations. The IOCG breccia subtype forms when a volume of fluid hits an impermeable trap at a fault intersection, creating intense overpressure. The pressure builds until the rock hydrofractures. This explosion creates highly permeable breccia pipes, allowing rapid fluid flow and metal deposition within shattered rock. The rare earth element, or REE subtype, deviates from the standard model. Instead of typical mafic rocks, the magmatic source is highly alkaline. Hunting for these REE variations requires abandoning standard gravity targets. The vectoring shifts to identifying distinct radiometric anomalies surrounded by sodic alteration halos. Even when driven by the same regional tectonic forces, differences in fluid pressure or magma composition will produce wildly different physical targets. Properly identifying the physical target is useless if the geochemical models are wrong. A persistent error in the industry is applying trace element models built for shallow epithermal or porphyry deposits to deep IOCG systems. This table outlines the resulting problem. Arsenic, antimony, mercury, lead, and zinc are excellent pathfinders for epithermal veins, but they are typically non-existent in high-temperature IOCGs. Relying on these elements produces false negatives. Teams hit nothing from their epithermal checklist and abandon viable targets. True IOCG geochemistry is anchored strictly by iron, copper, and gold. To vector toward the center, you must track the 5-star pathfinders: cobalt, bismuth, and tellurium. Modern exploration relies on cobalt concentration, a mathematically reliable indicator of fluid proximity. As cobalt rises, the distance to the ore chute decreases. The only major exception is uranium, a mandatory addition only when vectoring toward the highly oxidative hematite subtype. Hitting the drill target requires discarding outdated epithermal checklists. Accurate soil and rock chip vectoring relies on isolating that specific cobalt, bismuth, and tellurium footprint. Bringing this all together requires Bayesian prospectivity. This is the statistical reality that a single anomaly is rarely definitive. The probability of discovery only scales upward when independent, verifiable data layers physically overlap. Layer 1 establishes the plumbing. We isolate regional crustal lineaments to prove a deep fluid pathway exists. Layer 2 applies the gravity data. We look for heavy density anomalies resting directly over those faults, indicating iron accumulation deep in the crust. Layer 3 brings in the magnetics to identify the specific subtype. We need to know if we are targeting the magnetic highs of a magnetite trap or the magnetic destruction zones of a hematite system. Layer 4 utilizes Sentinel-2 satellite data, scanning the surface for the sodic or iron oxide alteration footprints that bleed upward from the trap. Finally, Layer 5 points us to the precise structural center by mapping the corrected cobalt, bismuth, and tellurium soil anomalies. Only when all 5 of these independent parameters intersect over a single geographic coordinate is the drill rig mobilized. Isolated data points are statistical noise. Stacking multi-parameter evidence is the only standard that justifies the multi-million-dollar cost of a drill program. This workflow takes the vast expanse of a continental margin and filters it down to a concentrated 50-meter ore chute. IOCGs are not a static template. They represent a dynamic spectrum of fluid evolution that requires constant analytical adjustment. Discovering them means stripping away historical biases, discarding the epithermal models, and trusting the physics governing each of the 5 subtypes. The reward for executing this precise, hypothesis-driven workflow is pulling a world-class copper and gold asset out of the basement rock. True exploration success is not found by chasing random anomalies, but by building rigorous, first-principles models that filter chaotic crustal data into high-probability drill targets.